he's actually a senior researcher here at the Aldinger Center for Energy and Environment. I think the building is attached to this building. And the title is Graphene Fundamentals and Applications. But before we start, I'd like to give some background. Mikhail received his Ph.D. in material science jointly from École Centrale Paris. Mikhail was born in France, right? And the École Normale Supérieure. Mikhail's French class is here, so they can help a little bit. The Cachan. Synthesis and applications of carbon nanotubes. And from there he went on to here in Princeton to follow a postdoctoral researcher at Princeton, a research position at Princeton University with Professor Ikan Aksey in the Department of Chemical and Biological Engineering. So he recently moved to the Aldinger Center where he is a senior researcher for energy and the environment. With that, we're ready for you.
Thank you, George, for the invitation and the introduction. So, as George mentioned, I am currently affiliated with the Aldinger Center for Energy and Environment and also the School of Architecture. I work in the group of Professor Forrest Meggers on energy efficient buildings. So we mostly try to develop new systems and materials to heat or to improve the heating or cooling systems in existing buildings. So, as George mentioned, I did my PhD on carbon nanotubes and their applications, so from the synthesis all the way to the applications, especially in polymer composites. And then I came here to the group of Professor Ikan Aksey, which his group pioneered the chemical synthesis of graphene, commonly known as functionalized graphene. So I will talk about the different ways and the different types of graphene, the way how they can be synthesized, and also a few examples of applications. So I would like just to start first with the question, what is the fate of carbonaceous nanomaterials? So if you do a search on ISI, just look for papers which have the title fluorine, carbon nanotubes, graphene. This is what you see. So since 2000 until last year, you see that the fluorine have been stagnating. So it's a plateau. There wasn't any big jump, specific year like for graphene or continuous increase for the case of nanotubes. Although the first synthesis and evidence for fluorine was made in 1985 by the team of Rick Smalley at Rice University, and the Nobel Prize was awarded in 1995. Nevertheless, you see that the numbers is around 800 and didn't change. But if you look at the nanotubes now, so nanotubes were first evidenced by Sunio Ijima in Japan, who is a transmission electron microscopist. So, although you can even often find that he discovered the carbon nanotubes, I think that's not true, because way before you can find papers in the 50s where Russian groups, for instance, I could go as far as that, where they evidenced this, what they called microtubule back then. So 1991, and then you see until 2010, roughly, nanotubes were popular. So what happens then in 2010 is the year when graphene got the Nobel Prize. And if you look at the graphene now, you see that although we knew it existed, but no one was really able to isolate it. But we were aware of such a structure. So 2004, the group of Andrei Geim and Kostya Novoselov at Manchester University were able to isolate it mechanically. So we'll talk in detail later about that. And they got the Nobel Prize in 2010, not for discovery or anything like that, more for the groundbreaking experiments that they carried out on this material, and namely the electronic transport properties of graphene. So that was what I will call pristine graphene, defect-free graphene, directly from mechanical exfoliation. And since then, you see 2006, it jumps, I don't know where it will end. So the question is, will it at some point reach a plateau like the nanotube, or will it continue? So that's an open question we can discuss at the end of the presentation. So the outline today, the outline of my talk today is, there is always a before and after to anything. So I will first talk about some basics that we need to know, because there is a story before graphene, of course. And then spend some time on discussing the different ways to synthesize graphene. Especially I will emphasize the chemical oxidation that was developed here, and give a few examples of application, and we'll end by asking a question, what will happen to graphene? So let me start off with graphite first. So everyone knows graphite, and actually I can perhaps say everyone is close to making graphene, from graphite, because the fact of writing is directly coming from the physical properties of graphite, with the hexagonal planes that can slide in the z direction. You see in the following slide. So everyone is familiar with this. Just to give you an idea about the different length scales we'll be talking today, because we will be talking about nanometric objects mostly. So this is the mineral, this natural rock, about 3-inch tall, that you can find almost anywhere, that has the graphite flakes that we'll be using for the synthesis of graphene through graphite oxide. So through sedimentation and well-known industrial techniques, you can separate, isolate by using the difference in the density between the two materials, the graphite flakes, which can reach almost a millimeter in diameter. And the ones that we'll be using for the synthesis of graphene oxide are ranging from 1 to 150 microns roughly. And this is the scanning electron microscope now, so we are going smaller in scale. Here the scale value is 200 micron from a graphite manufacturer, Asbury in New Jersey. So you see the plate-like structure of the material. So let's talk a bit about the structure now of graphite. So graphite has this hexagonal honeycomb structure. So each of these planes is one graphene layer. And so you have covalent bonds between the different carbon atoms here, and the separation, the bond length is roughly about 1.4 nanometers, so 1.4 angstrom. And the distance between the planes in the z direction is about 0.3 nanometers. So keep that number in mind, because we will use it later. So I said graphite has many interesting properties. It's because of the physical and chemical properties that it has. As you can see on this phase diagram here, you see that it's stable up to almost 3,500 Kelvin, which is extremely high temperature. So it's clearly one of the most stable materials, and at a reasonable pressure. And when you go actually even higher in terms of pressure and sufficiently high temperatures, you can even synthesize synthetic diamond if you follow that logic. So now, if we look more carefully at the properties, let's first look at the electrical properties. So I'm going to give you the resistivity of the material and have a comparison with a well-known material, copper. So you see that in the AB, in the planar direction, you have a quite low resistivity, 10 to the minus 6. Just comparison, copper has 10 to the minus 8 ohm meter. And that's mostly due to the fact that you have 3 carbon atoms in this plane, and then if you go in the Z direction, so in the C direction, this way, the conductivity is low, resistivity goes up. Why? Because you don't have an electron exchange or mobility in that direction that is being favored. And if you look at the thermal conductivity, we have more or less the same logic, but we have to talk about the fact that you have less favorable lattice vibrations for the phonons in the Z direction. That's why the thermal conductivity is quite low, 2 orders of magnitude lower. But you can reach something close to copper. And diamond, for example, has 2,000 watts per meter Kelvin. If you look now at the mechanical properties, again, you can have quite an interesting number in the parallel to plane direction. It's not too far from metal. So that's, and plus combined with an external resistance to chemical reactions in the basal plane, this provides a very good field of applications for graphite. So just to give you a quick also overview about the nanotubes now that we mentioned at the beginning. So the nanotubes have attracted a lot of interest until 3 or 4 years ago or 5 years ago. Mainly, I assume because of the impact and the room taken by graphene. And it got very popular. So the way how you synthesize carbon nanotubes is mostly through chemical vapor deposition, although laser ablation of a graphite rod was the initial experiment that Sumio Ichima did in Japan when he was imaging them. But the CVD has the advantage of being easily scalable at industrial scale. So you have companies today, many companies in Europe here, commercializing carbon nanotube in bulk quantity. So the way how you synthesize, the CVD process works, you have a carbon source such as iodine in this case, which is dissolved in ferrocene. Ferrocene will serve as a catalyst for the carbon nanotube growth. And you inject it into a reactor at relatively high temperatures, at least 600 degrees C, in a protected atmosphere. And on the silica substrate here, you would have the growth of carbon nanotube mats. So this is the way how they look like. And unfortunately, this configuration makes it difficult for ultimate use. Whereas in the case of carbon fibers, the way how they are synthesized from polyelectronitrile is very well controlled, so you have perfectly aligned fibers, etc., that come as a textile. So that's, I think, aligning the carbon nanotubes and dispersing them because they tend to aggregate due to van der Waals forces is a big problem that we also have with graphene. Not really alignment, but more the aggregation. And here's an example of application of the carbon nanotubes. So you can grow them on ceramic substrate very easily. So what we did, because we knew that there was dispersion issue, so we took the ceramic particle alumina, in this case alpha phase alumina, micron size, and we grew the nanotubes on top of this particle. Why? This gave you a better way of controlling the dispersion of the tubes inside an epoxy matrix, for instance. And as you can see on the plot here where we show the thermal conductivity as a function of carbon nanotube weight fraction, if you don't use the silica part, the alumina particle, you see this is without any carbon nanotubes. You see that we reach somehow good conductivity, better than the polymer alone, but you don't really see a huge increase in the thermal conductivity. Whereas if you use now this type of configuration, so you combine a micro nano structure, you see immediately a sudden jump in the conductivity. So this is quite significant result, 0.4 watt per meter Kelvin at only 0.15 weight %. So nanotubes were interesting, but they kind of lost the race with graphene. Just before going to graphene, I just want to give you a few important dates here. So it goes back to middle of 19th century when Brodie at Cambridge in the UK was able to chemically produce graphite oxide. So he was already able to oxidize graphite from the edges and intercalate the graphene sheets with functional groups, oxygen-based functional groups. Then, about 40 years later, Staudenmayer came with his own technique to synthesize graphite oxide. So he revised, he revisited the acids mostly and introduced some new salts until Hammers came again about 50 years later with his own way, with slight modification to the process. But then it was dormant. No one really had the idea, or we didn't find the idea of going further and splitting apart these graphite oxide sheets. So until 2004, when Geim published his groundbreaking experiments on the mostly electrical properties of pristine graphene, defect-free graphene. And then here at the university, my former group, the lab of Professor Oxide, same year, the lab of Rolf in Texas, they came up with a way to manufacture graphite oxide in large scale, but then also continue further and get functionalized graphene sheets. So functionalized graphene sheets, you have to be sure that you separate it from pristine graphene, which is the defect-free graphene obtained by Novoselov. So those are the two types of graphene mostly on the market we have to deal with. And ultimately, in 2010, Geim and Novoselov got the Nobel Prize. So let's start with the way Geim and Novoselov produced their graphene. So when we say mechanical exfoliation, it's a very simple process. So you can even do it at home if you are patient enough. So take a block of graphite, tape it on silicon, for instance, and apply a thin scotch tape and repeat the operation 100 times, 500 times. Can be a good game for kids, for instance. I would try to ask my son to do that. And ultimately, if you dissolve the organic tape and transfer the film on it onto another clean silicon substrate, say you can start working, or silicon dioxide, you can start working on it and characterize its electrical properties, for instance. That's the way the Geim group in Manchester operated. And here you have transmission electron microscope images. So the one on the left is the image acquired as it is on a high resolution TEM. So you have the graphene layer starting here. You can kind of guess the honeycomb structure already. And then you have a second layer here on top of the first one. So you can see a contrast at the boundary between the two. And then with recently very powerful TEMs now with several lenses to correct for aberrations, stagnation, etc., you can even get images like that almost. This image has also been processed further with Fourier transform, etc. And if you remove the background noise, so you can resolve now the individual atoms. And at the university here, we also have a microscope that can do this type of imaging now. Another way of characterizing the material, so what's important here is to make sure and convincingly prove that we have a single layer. So another way, but slower way, is the use of atomic force microscopy. So the idea is to come with a very sharp and hard tip and scan a surface and resolve the imaging from the height profile. So this is a functionalized graphene that was made in our lab. And when you look at the height profiles, so here you see we are almost at about 1 nanometer, and the functionalized graphene produced here at the university has about 1.8 nanometer height, whereas pristine graphene, the one made by Bozlar from mechanical exfoliation, has a thickness about 0.7 nanometer. So where is the difference coming from? It's simply coming from the fact that we have functional groups and we have a defective graphene, in other words, in our case. So we'll go to that later in detail. That makes 1 nanometer of difference between the two. And then you can see it goes all the way up to 5 nanometer, and this is coming from this unique property of graphene, this compliance. So it conforms to any surfaces you put on. So, and if you were to synthesize it and disperse it in a solvent, for instance, during evaporation and drying, the capillary forces would attract, and the graphene film will bend, basically. That's why you can reach as high as 5 nanometers. So again, keeping that importance of justifying the presence of single layer in mind, another way that was developed again by the Manchester group was the use of Raman spectroscopy. So this is the spectrum for graphite. So it has the two characteristic peaks, here the G band and here the 2D band, which is clearly a signature of its electronic structure. And graphene has also two nice peaks at the same location. So now, if we focus in particular to the 2D band, you see that when we have single layer, independently of the excitement, you can use the green or the red wavelength, you have the same conclusion. So it's not an artifact of the excitation source. You see that in the case of a monolayer, you have a nice sharp peak. As soon as you start having two layers, you have now a broader peak with a shoulder. So why? This is simply due to the electronic structure of graphene. And so as you go up further, up to 5 layers, for instance, you have also the shift. And clearly, this peak and the shoulder are not changing anymore as soon as you exceed a few layers. So together with that, so now if we talk about the properties now, if we first focus on the mechanical characteristics, the way how this intrinsic very high skill required here for those type of experiments, because you have an insulating substrate, say, then you need, through, for instance, photolithography, make holes, trenches, and then suspend a graphene layer, and then you can start working on it. You can measure the mechanical properties of the material, just like a simple tensile experiment. So basically, you would apply a load and measure the deformation of the material. And from that, you can get the stiffness of the material and the tensile strength. And it turns out that a group at Columbia recently measured a modulus as high as 0.5 terapascal. So if you go to ab initio calculations, the predictions are even going up to 1 terapascal. So this is way higher than any steel. And the tensile strength is also impressively high, 120 gPa. And so it's following kind of the same architecture. The thermal conductivity was measured by a group in California, Los Angeles. So they suspended a graphene and then they excited with a micro Raman probe, and using different output powers and calculating different, they were, in general, globally, they were able to estimate the thermal conductivity about 5,000 watt per meter Kelvin. So this is way higher than nanotubes, about 3,000 watt per meter Kelvin, higher than diamond, 2,000. And what is also of interest, and this is one of the major contributions of Gaim and his team, is the electron mobility. So electrons just travel as if they have no mass across the graphene film. And this value of 10 to the 4 competes with copper, which is only about 10 to the 3 centimeter square per volt second. So very interesting properties intrinsically. So clearly the mechanical exfoliation has the advantage of allowing you to get a good model system to study very precisely the intrinsic properties. But it lacks in terms of scalability, but also the irregular quality and the size of the pristine graphene that you can obtain this way. So very rapidly after the Gain work, 2004, several ways have already been explored. Chemical exploration, actually, I would have put it here first. CVD came up a bit later. So let's start with the CVD. So CVD, chemical vapor deposition, consists of having a substrate. As you have seen in the case of nanotubes, we had silica, we had a non-reactive substrate, stable at high temperatures. Here we use copper because it's highly reactive, and so when you bring this material at 1000 degrees C roughly, and you inject a carbon source such as methane in the presence of carrier gases and in an inert atmosphere, you start breaking the structure and forming the hexagonal structure of graphene. This is, again, a perfectly defect-free graphene, just like the one obtained directly from graphite. And then what do you do with this? That's the problem. You have a substrate now, it's a metal. You can handle graphene directly. So what do you do? This work was developed by the university in Korea in collaboration with Samsung. So what they did, they transferred the graphene from the copper onto a polymer first using a roll-to-roll mechanism. And then they etch the copper away, and ultimately they release the graphene layer from the polymer to the target substrate. In this case, it can be another polymer, or it could be glass, anything. So it has several advantages, CVD. You can have 30-inch in diameter graphene films, which is impressive. And then it's transparent. And then it has decent electrical properties. So if you compare here the properties of graphene, so here we are measuring the change in the resistance as you are stretching your material and normalizing. You see that in the case of graphene, as you are stretching up to 6%, just to give you an idea, 100% would be you deform the object by twice its initial size. So 6% is still low, but anyway, the resistance doesn't change. Whereas in the case of indium tin oxide, which is commonly used for its transparency, if you have an indium tin oxide coated polymer, as soon as you reach 3%, you lose a lot of conductivity. So there's interest there, but again, this technique has some limitations. And why? Because it's a multi-step process. You always need a substrate. Substrate is not necessarily good unless you are in the electronics industry. You are making transistors, but if you want to make bulk objects like these polymers, etc., it's not the best. And the high temperature is also not ideal. And all of that sums up, and you have high costs. So, however, despite that, very recently I found a group in Korea, again, they came up with a plasma-enhanced CVD. Again, plasma-enhanced CVD is not new. For the nanotubes, it has already been widely used. And doing that, they were able to synthesize graphene, pristine graphene at room temperature, which is very interesting. So now, I will talk about the other route, the chemical exfoliation of graphite to obtain functionalized graphene, so the defective graphene. We start first with graphite flakes, and you oxidize them in the presence of acids and salts. Then you carry out this reaction at relatively low temperature, about 50 degrees C, and then you proceed to the washing of this brownish now suspension. And when you dry it, you obtain this brownish powder. So at this stage, we call it graphite oxide. So imagine you have planes of graphene now, which are expanded with oxygen functional groups in between them. So what do you do is that we are not really at graphene yet. And so my former group came up with this innovation. They heated this material. So when you heat it under a protected atmosphere at about 1000 degrees C, ideally, you can effectively separate those graphene oxide sheets. And in the end, you have what we call functionalized graphene. Okay, so it looks like this. So this is a 20 ml vial, which has the graphene powder. And this is an SEM image from the study back then in 2007 of crumpled graphene sheets. So just let's discuss a bit more in detail the properties of this oxidation process. So remember we said 1898, Staudenmayer came up with his synthesis using sulfuric, nitric acid, and potassium chloride. Hammers suggested to use sodium nitride and potassium permanganate. And more recently, a group at Rice University further developed that technique by using phosphoric acid and came to have an even better yield in terms of oxidation. However, overall this process is very sensitive. So you have to carefully control your parameters, concentration of your acids, temperatures, durations, etc. So this is on the left an XRD study, again with the goal of showing that we have indeed successfully obtained graphene. This is we're starting graphene flakes of 400 or 500 micron in lateral size. So at the beginning, before the oxidation starts, you have the native graphite peak at 0.34 nanometer. That is the signature of the different lamellar structures. As the oxidation process starts, you see that the signature, the fingerprint of graphite goes down, and you have another peak appearing here. This corresponds to a separation of about 0.7 nanometer now. So that is the indication of you are now exfoliating your graphite. However, you see that you still need to go quite to high time durations. But if you now use a smaller size graphite flake, what happens is that after 48 hours, so you have already improved the yield, you start seeing the signature of graphite oxide, which is also an important parameter to consider. So, of course, this is at the beginning, 2007. It has been further modified and improved. Here are some images of the material synthesized here in our lab. So you have just for your record, you have graphite here again with the perfectly aligned lamellar structure. This is graphite oxide. You see it's already becoming a mess. So what's happening here? This is simply due to the fact that we have now all these functional groups in between the different planes. So from this material, as I said, if you heat it further under near atmosphere, you can get what we call functionalized graphene sheets. So those are now individual graphene sheets that are highly functionalized and also have lattice defects. But we'll see that those are not necessarily bad for us, because the presence of functional groups in the basal plane, such as epoxy or hydroxyls, or at the edges, carboxylic acid groups, actually help you if you want to do chemistry with them. So if you want to, say, embed them in a polymer matrix, you may have a chance of having a better compatibility than using pristine graphene, defect-free graphene. And also of importance here is, so because the process itself is a highly energetic process, you lose some carbon, and the splitting of the graphene layers actually is coming from the fact that you have CO2 built up. So as you are releasing CO2, what happens, you have some vacancies here. So as you can see here, we are losing carbon atoms. And it gives you these big holes in the basal plane of the of the material. Okay, so we have functional groups and we have defects. If you look now at the physical properties of this material under the AFM, so this is the material that has been heated, you see that if we look at the population that have a thickness range of about 1.8 nanometer is the majority. So that's the value we are taking on as a reference. And if you look at the dimension now, the diameter of this graphene sheet, you see that they mostly range on the order of a few hundred nanometers. So you can also have graphene sheets that can be as high as few tens of microns. But it's never going to be hundreds of microns due to several reasons. One of them is the initial graphite plate size that we are starting with, and then you are limited anyway in your process because of the periodic cracking of the graphite plate. So here, I wanted just to make sure we are all on the same page and clarify that here we have, it's actually an STM image, scanning tunneling microscope image of HOPG, so it's highly ordered periodic graphite, but it has the same structure as pristine graphene. So as you can see, you can have a clear view of the hexagonal honeycomb structure. But now if we look at our material, the functionalized graphene, what's going on here? It's really a mess. It doesn't look as pretty, right? So why? Again, this is coming from the fact that we have all these defects, we have all these functional groups, so you can't really resolve. But if you were to go further, you would, of course, find some clean and defect-free regions. But in terms of scale, they would be smaller. And the proof that we have a honeycomb structure, if you do the Fourier transform of this image, you can reconstruct the hexagonal structure. So as I said, the fact that this material is highly defective and has a lot of functional groups is actually good in the sense that it allows you to do some chemistry with it. So we have been able to show that if you take this type of material, highly energetic with a lot of nitrogen in it, you can, through nucleophilic substitution, get rid of the chlorine bond here and attach it to two graphene layers and covalently link them. So we have demonstrated the covalent linkage using different techniques, and here AFM is one of them. If you look at here in this case it's going to be graphene oxide, which has a carbon to oxygen ratio of 2. I will come to that in the next slide. You have a height about almost 1.8 nanometer that we are discussing. But as soon as you start doing something with it, you see we are reaching a height of a micron. So there was clearly something happening during the leakage. So with functionalized graphene, also known as FGS, a very important parameter is the carbon to oxygen ratio. So we use this as a proxy to verify the degree of reduction of the material. So as you can see, the carbon to oxygen ratio is going up as you are heating the material, exfoliating at a higher temperature. So what you are doing when you are doing this, you are clearly getting rid of some of the oxygen functional groups and changing the hybridization in the structure from an sp3, you are getting more and more sp2 network, which render the material conductive in the air. So along this heat treatment, because you are changing the chemical structure, this can be evidenced also if you do contact angle measurement. So on the left here, you have the graphene with a low CO ratio, so 5 or less. It's it's hydrophobic, so it wets the surface quite good. I mean, water wets the surface of graphene quite good. So. But as you are reducing your material, you see now the angle is going up, 87. It becomes hydrophobic. Why? Because you don't have those groups anymore that like water. Okay, so the advantage of functionalized graphene is multiple because you have more way of tailoring its structure. Whereas graphene obtained by the mechanical exploration doesn't give you that luxury. So now I just want to give a few examples of applications in polymers, graphene as a gas barrier, and also give you an example of its use in energy storage devices. So here we are looking at the conductivity of a polymer composite as a function of the carbon black loading here and graphene here, functionalized graphene. So you see that at the beginning when you have a very small amount of graphene, the conductivity is about 10 to the minus 14, 13 Siemens per meter, which is the conductivity of the polymer. But as you reach a critical concentration, you have this sudden jump in the electrical conductivity. This is the percolation threshold. And then the increase is not there anymore, but you would anyway saturate because you won't be able to add more graphene or fillers in any case, depending on the intrinsic properties of the fillers, of course, because the viscosity is going to go up. So faster, in certain types of carbon blacks than in others. And in the case of graphene now, so what's happening is here, you see that the percolation threshold is 3 times lower in this case. We have the percolation taking place at 0.03 versus 0.09 in the case of carbon black. So this is an interesting type of applications of the graphene and carbon blacks for comparison. I forgot to mention it was in polydimethyl siloxane, so a soft silicon elastomer. So the use of graphene has been in anything you can imagine. I have even seen papers with graphene on cement, so it goes to anything. This is a study done by Gaim's group. So for this purpose, because they are aware that mechanical exploration cannot go too far, so they use also the oxidation of graphite to produce graphene oxide suspension. Then they coat a substrate like copper in this case, and then they make a trench again here so that graphene here can be accessible after etching with nitric acid. So they end up with this material. So what you see in the center is a graphene membrane that will be tested. So it looks like this, and it's collected through filtration. Very simple experiment. You have a suspension of graphene, you filter the solvent, and it forms a nice film like that, with thicknesses on the order of a few hundred nanometers up to a few microns. So in the first experiment, what they did, they test a liquid, water, and other solvents. So they basically, what they do here is they record the rate of evaporation of the solvent through the graphene membrane. And interestingly, what you see here, so this is the control experiment. When the aperture is open, water goes through at a very high rate. If they use now the graphene as it is, directly after graphite oxidation, you also have a very high weight loss. So what the membrane made out of graphene oxide is not a barrier. But what happens now if you reduce the material, so thermally or chemically using hydrogen, for instance, what happens, you see that now water doesn't go through anymore. Why? Because you don't have, or you have less of these functional groups now between the basal plane of your graphene film. So this film, just to clarify, it's not one graphene sheet, it's many sheets on top of each other. But they have functional groups which are compatible with water, which like that's why it's hydrophilic. So, but if you get rid of some of these functional groups, you see that you can indeed now have a selective filtration. So water doesn't go through, neither does hexane and ethanol, but in the case of GO, not reduced GO. So it's important here. When you don't reduce GO, you cannot have. So for filtration purposes, for water treatment, etc., this can be very interesting because you won't let large solvent molecules go through, but water will go through if you tailor the properties of the graphene oxide. And similarly, they did the test with gases like helium, H2, N2, and what happens there is that when you have the non-reduced graphene oxide membrane, you have no leak, so nothing goes through, or very little. But if you use a conventional polyethylene terephthalate membrane, where you have your water, like the gases can easily go through. Another example of application of graphene in energy devices is in batteries. So just an example of lithium-ion batteries, the way how they work. So we have a positive electrode, also known as the cathode, and a negative electrode as the anode, which has the active material. In this case, is going to be graphite. On the cathode, you would have a metal oxide active material. So the idea is, the working principle is you shuttle lithium ion back and forth depending if you are charging or discharging your battery. So if you are charging your battery, so these red lithium ions would go migrate to the other electrode, the anode, and interpolate between the graphene planes of graphites. So that's a good chemistry. But what happens now, and in between, another important component is the separator will hold shorting, and in the presence of the lithium source, the electrolyte. So what happens now, if you take a lithium metal electrode in the anode, what happens is you have side reactions that take place as you are charging, discharging your battery, and as a result, you have a limited lifetime of your battery. Why? Because you grow dendrite that can pierce through the insulator and short your cell. That's not good. Or another type of reaction is that the lithium metal electrode would react with your electrolyte and form porous lithium. And that's not good neither, because it's going to increase the overall resistance of your system. So the idea we had was to have graphene coating in between the separator and the lithium metal. And why is graphene interesting here? Because it can allow lithium ion to shuttle back and forth while preventing the electrolyte being in contact with the lithium metal. So all of this was with the objective of improving the cycle life of the battery. So if you look now at the capacity, discharge capacity, taking into account the first cycle as the basis, you see that when you have a bare lithium anode, you lose discharge capacity goes to less than 80% after 100 cycles, whereas if you use a graphene protected anode, it allows you about 25% or so increase in lifetime, which isn't bad. And together with the increase in the resistance on the right one, and minimized when you use graphene. The resistance increase is minimized when you have graphene. So, and the evidence for that is, so on the top here we have the non-protected lithium metal electrode. So at after 5 cycles, the cycling rate was 1.5 milliamp per centimeter square. You see, you have the formation of this film here, which is bright. That means not conductive. It's a scanning electron microscope image, so that's not good. Whereas in the case of the protected electrode, you don't see it or barely see it. You see a little bit here. And if you go further in terms of cycles, so you put your system onto more constraint, under more constraint, you see that after 25 cycles, this is now reaching over 50 micron in thickness. So all of this is useless material. And again, in the case of graphene protected material, you barely see it, or less. So to wrap up and open the discussion, perhaps, just would like to ask this question. So what will happen to graphene? If you remember the plot I had at the beginning, because now we have new type of materials, such as silicene. So if you look at the periodic table there on the same top, silicene or germanium, which have very similar structure or identical structure, honeycomb structure to graphene. So, and this material, there are already simulations and also experimental measurements demonstrating that they can compete with graphene in terms of charge carrier mobility and also mechanical properties. So the only issue here, and maybe it will be trigger for further work, is the synthesis of these materials. So you start with silicon, which is quite stable, then you have to synthesize silicene, you need to basically evaporate, vaporize silicon onto a noble metal like silver or gold at extremely high temperatures and vacuum conditions. So, in other words, as we saw, because the graphene made through mechanical exploration could not really go too far, I guess if there is a way to synthesize it, for instance, chemically at larger scale, it may trigger a competition for graphene. And with that, I would like to acknowledge my previous lab and the startup I was working for and the funds through the Army Research Office at the beginning of my postdoc, the RFIE more recently on the graduates, and the French Embassy, and also my group, the Chaos Lab, led by Forrest Magers. I'd like to acknowledge them for their support. So, yeah.
Any questions?
Have the silicon and germanium analogs been synthesized or not?
Yes, they have. So this is.
At the next down?
Oh, I'm sorry, an additional one? Yeah, yes, so there is molybdenum sulfide, MOS2, that also has a hexagonal structure. That's also being, it's the subject of intense work too. But compared to graphene, it's still peanut because I think the investments are not the same. Just the European Union invested 1 billion euros, 3-4 years ago. So, and it's clearly occupying a bigger market, graphene. But I think the way how to synthesize the material is a big concern here, because if you think in terms of industrial application. So I think that's the major parameter here. That's why I emphasized the talk about the synthesis.
Can you summarize in a short period of time at all what it is about graphene and where we are at this point? We were trying to get to, and are there any other materials? We're basically saying there are no other materials beyond graphene. You have some structural traces here, like silicon, and so forth.
Yeah.
Where are we headed?
That's my question. So I think it's a difficult question. I don't know if I can answer it, because I don't know what will happen tomorrow. But in view of, I think the investments, mostly graphene is, I think, ahead of everyone. But I personally think that we have, reached some limits.
Ahead in what way?
Graphene is ahead in terms of number of people working on it and number of investment in terms of research. So it's way further ahead than germanium or silicene. But yeah, I personally think we have kind of reached the limit because it's been some time now. And can you buy something made out of graphene? Can your bicycle be framed maybe out of graphene? So the question is why? So then it comes again all to the handling of the material and controlling the usability of its properties, etc.
Is there any particular property that you're trying to get better so that you can make a better bicycle, say, or something?
So
Did you say
I
anything
think
like that?
I think the material intrinsically, if you isolate it, it's not bad at all. And I think that's why people are calling it a wonder material. But what do you do with it? Because you can't do anything, it's a powder. So you need to combine it with something else. And as you have seen, you can improve the properties of the polymer, but not necessarily to the level you want. And why? You are limited then in terms of processing, for instance. You would increase, for instance, in a polymer composite, the Young's modulus too much. You don't want that because you want a material that can stretch, maintain conductivity, but you don't want it to be too hard. So, but to make it sufficiently conductive, you need to add a lot of graphene. So there are all these parameters that kind of make the stuff complicated. And nanotubes, there was a lot of extensive research on it, and it kind of stopped now. So the knowledge, there was already a knowledge from the nanotube that we could take and use it for graphene, but despite that, still not much, right?
I have a question. No. So it's amazing how sophisticated some of the work we presented is today. The instruments. The first work in the 1800s, they didn't have any instruments. And they probably didn't understand chemical structure that well. How did they know what they were doing?
Yeah, I always admire these people because,
There was an
1898 or in the 50s, I found a Russian study where they had nanotubes back then, but we had to wait 1991 for Ijima to use electron microscopy. So clearly, I think some of the advances we are describing as discovery, I think are not really, they were there, but we just couldn't see them.
They didn't know what they didn't know what they had.
So they knew, Brody, 1898, knew that he oxidized graphite. Because back then, what could he do? He couldn't do TEM, he could just burn. Fire, everyone had fire. So he could burn and do a mass analysis. And from there, he was able to back up and say, okay, I have introduced oxygen now into my system. So, yeah. But yeah, I do admire, I want to emphasize that. We are talking about nanomaterials, etc., but they were actually there. I mean, just to give you the example, sorry, of the fluorine. So when Harold Kroto and Smalley wrote the Nature paper in 1985, there is a sentence in the Nature paper, I just read it again yesterday. He says, I foresee that this material is everywhere in the universe. And very recently, just 2 years ago, the mix of European and American groups did indeed confirm with the Fritz telescope that you have fluorine, outside Earth. So, yeah, I think there is a lot of knowledge that was already there, and we are rediscovering.
Molly was here in the Princeton.
He was at Rice University.
But before that, he was at Princeton.
Oh yeah, he's an yeah. Sorry.
If you think of graphene as a kind of a higher polymer or fairly pyrene, carbon, aromatic carbon is very well known.
Yeah.
You put the rings together and get very good figure. Is there any chemical evidence for double bond aromaticity in silicon?
With silicon, that's a good question, Brian. I am not sure because I haven't investigated silicon too much. I'm investigating heating and cooling systems now. Okay, we can. I would be happy to discuss it with you. But
I think somebody made an aromatic ring with silicon. Recently. Very recently.
yeah, I haven't gone that way too much. just recently, like out of curiosity, but yeah, it is an interest to explore that. Yeah. So.
Well, you've partially answered the question I was going to ask. What applications are you investigating that would apply to architecture?
So, well, Forrest, are you interested by graphene in architecture? Why not?
Well, that's what I was going to ask, whether you think that there's three domains that you mentioned. There's electrical, then there's structural, and then there's chemical. And I mean, from a architectural point of view, you think structural will be the first thing, but actually I think the chemical domain is more interesting because of the ability to do filtration and to manipulate its interaction with air streams or streams you're trying to manipulate in the building domain that are much more energy intensive. For example, air filtration or managing those systems, because the membranes we use now are very difficult to deploy and use a lot of energy. So I think actually the chemical part is more fascinating. But I mean, my question on the chemical side would be, how sensitive is this stuff to the number of layers? Because it seems like there's two domains. There's like the singular layer domain, and then the membranes you mentioned are all multi-layer. And then what happens to those functional groups when you do start to add water into them or not? And does that change the ability of the graphene to continue to function as a membrane?
Yeah, so just before I forget, I will answer your question, but related to heating in a building, I just found out a TED talk where another group, in Europe was exploring the use of graphene in architecture. So it's not, we are like half joking, but it's not that a bad idea because they were exploring, for instance, yes, exactly, like chromate, exactly. So you would, everyone, for instance, at the public library, my wife works at the public library, and when we go there, you have these electric, lines that go up, and then you are blind.
Yeah.
So
Smart window.
yeah, wouldn't you want? And it's not too difficult, right? The physics behind, you measure the amount of light absorbed, and then depending on that, you can have an electrochromic display and make the window darker, or even just trigger, the blinds, right? Would be better. So I think it's not completely a dead story, the use of graphene. We just have to come up with a feasible, because people have tried a lot of things. Just yesterday, the issue of science was, the recent weekly issue of science was describing the reduction of graphene with a DVD player. So I think if we can manage finding some good and feasible ways, why not in architecture? Yes, I would be happy to go that path too. So to respond to Forrest's question, so let me clarify if I didn't answer properly, but let me understand. So when we have a membrane, clearly we don't have a single sheet. We have multiple sheets on top of each other. Okay, and in one case, the group, Gaim's group, used graphene oxide, so which is the non-reduced material. Okay, so when you don't reduce it, you just use it with the functional group, so you have now layers of graphene, and in between you have a small separation, right? Oxygen atoms. You have water that goes through, but now if you heat this, so you basically get rid of the oxygen groups, you make the graphene sheets collapse, right? So the graphene structure has changed because you not only have removed these functional groups, but you also have changed the lattice of the base of plane. So that makes it less compatible with water, and therefore you can have now an effective barrier for water. Did I respond? So it's a significant advantage, the fact that you can tailor and play with the properties of graphene obtained by the mechanical route. Whereas the mechanical, the one obtained by mechanical exfoliation, you are stuck, you can do much. It's a very stable and perfect structure.
Okay, we think if we have no more questions, please join me. Thank you.
Would our award winners please come down front?
Please stay here for the picture.
We would